Today I will discuss the proof of Cauchy-Schwarz inequality by using second method and third method. The statement is if a1, a2 up to an and b1, b2 up to bn are real numbers, then we need to prove the square of summation I from 1 to n ai bi is less than or equal to summation I from 1 to n ai square into summation I from 1 to n bi square, or we say that equivalently we can say that mod of summation I from 1 to n ai bi less than or equal to root of summation I from 1 to n ai square into root of summation I from 1 to n bi square. The proof is given by, since we know that the geometric mean of any two non-negative real numbers a and b is given by root of ab, which is less than or equal to their arithmetic mean, which is a plus b by 2. So if we have non-negative real numbers x1, x2 up to xn and y1, y2 up to yn, then we have in the same way for x1 y1 less than or equal to x1 plus y1 over 2, and so on for the non-negative real numbers x and yn less than or equal to xn plus yn divided by 2. So these are n number of inequalities. When we add the left hand sides and right hand sides of these n number of inequalities, we get summation I from 1 to n root of xi yi, which is less than or equal to summation I from 1 to n xi plus yi over 2. This is our equation number 1. I just added the left hand sides and right hand sides of all these inequalities. Now I would remove this one. Now we suppose that a is equal to root of summation I from 1 to n ai square in the same way. I shall write b, which is root of summation I from 1 to n b I square. Since our equation 1 is true for all non-negative real numbers, so we take uh, xi in this way, which is also our non-negative real number. We choose xi like that. Xi is equal to ai square over a square, and we also take alternatively yi, which is or which is our bi square over b square. So as you can see, xi and yi are also non-negative real numbers. So when we put these two xi and yi in our equation 1, by putting in 1 we get summation I from 1 to n root of ai square over a square into bi square over b square less than or equal to summation I from 1 to n. Xi is ai square over a square plus bi square over b square divided by 2. We just put the value of xi and yi in our equation 1 to get this inequality. So we have, by simplifying, summation I from 1 to n ai bi whole square over a b whole square under root less than or equal to 1 by 2 is independent of I, so we take out 1 by 2 outside, and what is left inside, we have ai square over a square plus bi square over b square. Then we have summation I from 1 to n, and this is equal to a root of a I b I whole square over a root of a b whole square, and this is equal to, and this is less than or equal to, sorry, this is less than or equal to 1 by 2 summation I from 1 to n ai square over a square plus summation I from 1 to n bi square over b square. The summation is separated over this term and this term, which is very simple. So this term is independent of I, so we can take out, and this is equal to 1 by ab summation I from 1 to n, and this is equal to root of ai bi whole square less than or equal to 1 by 2, and here a square is independent of I, so this is equal to summation I from 1 to n ai square over a square. In the same way, we have summation I from 1 to n bi square over b square. Here, that's equal to 1 by ab, and since we have a root of x square equals to mod of x, so we can write here mod of, sorry, summation I from 1 to n mod of ai bi less than or equal to 1 by 2, and what is over a? A is root of summation ai square and b is root of bi square. So this term, this numerator, this is equal to a square and this numerator is equal to b square. So we have a square over a square plus b square over b square, and this is equal to 1 by 2 multiply by, that's equal to 1 and that's equal to 1, so 1 plus 1, and this is equal to 1 because this is 2, so 2 will be cancelled with 2 and eventually we get 1. So here also we have mod of AB. So this implies that 1 by AB mod into summation I from 1 to n mod of AI BI less than or equal to 1, and this implies that summation I from 1 to n mod of AI BI less than or equal to mod of A into B. As we know that A and B, what are A and B? A and B are non-negative real numbers because A is equal to summation A is equal to root of summation AI square and B is equal to root of summation BI square. So A and B are non-negative. So as A and B are non-negative, therefore AB is also non-negative. Since A and B are non-negative, we deduce AB is also non-negative. And since we know that mod of x is equal to x when x is non-negative and minus x when x is negative. So as we know that we have this inequality which is named as 2. In this inequality, the inequality number 2, we get summation I from 1 to n mod of ai bi is equal to, is less than or equal to, is less than or equal to a into b, because mod of ab is equal to ab. By using above definition, because our ab is non-negative, so mod of ab is equal to ab by using the definition of modulus of x. As you can see here, this is mod of ab and ab is non-negative, so mod of ab is equal to ab. As we know that for all real numbers x, y, mod of x plus y is less than or equal to mod of x plus mod of y. So by using this inequality, we have summation I from 1 to n ai bi less than or equal to summation I from 1 to n mod of ai bi, because we apply this inequality mod of x plus y is less than or equal to mod of x plus mod of y. So by using this inequality, we have mod of summation ai bi, which is less than or equal to summation I from 1 to n mod of ai bi, because we have ai, sorry, if we have a1 b1 up to so on an bn, its mod, which is less than or equal to mod of a1 b1 up to so on mod of an bn. So when we write in the summation form, we get this inequality mod of summation ai bi less than or equal to summation I from 1 to n mod of ai bi, and this is less than or equal to ab. This implies that mod of summation I from 1 to n a I bi less than or equal to ab. So mod of summation I from 1 to n ai bi less than or equal to, what is a? A is root of summation I from 1 to n ai square into b. B is root of summation I from 1 to n bi square, which is our required Cauchy-Schwarz inequality, hence proved. And this inequality is proved by using second method. For the now we shall prove Cauchy-Schwarz inequality by using third method. Proof: let Sn is equal to summation I from 1 to n ai bi square minus summation I from 1 to n ai square into summation I from 1 to n bi square. We name it as 1. Consider Sn plus 1 minus Sn, which is equal to I from 1 to n plus 1 ai bi square minus summation I from 1 to n plus 1 ai square into summation I from 1 to n plus 1 bi square minus the value of Sn, which is summation I from 1 to n ai bi whole square minus summation I from 1 to n ai square into summation I from 1 to n bi square. We just put the value of Sn plus 1 and Sn. So what we do here, in this term we break the summation in two terms. We break this summation in two terms. The first term consists of n terms and the second term consists of an plus 1 bn plus 1. So we have summation I from 1 to n ai bi plus an plus 1 bn plus 1 whole square minus, again we break this summation into two terms. First, for the summation of n terms, I from 1 to n ai square plus a n plus 1 square multiply by, again we break this summation in two terms. The first consists of summation of first n terms summation I from 1 to n bi square plus b n plus 1 square minus, we have summation I from 1 to n ai bi whole square. We multiply minus with this bracket when we multiply the minus sign, we get plus I from 1 to n ai square into summation I from 1 to n bi square. We can also remove this bracket uh, because we don't need this one right now. So we expand by using the formula a plus b whole square. When we apply the formula a plus b whole square in the first term, this one, so what we get? We get summation I from 1 to n ai bi whole square plus an plus 1 square bn plus 1 square plus 2 multiply by summation I from 1 to n ai bi into a n plus 1 bn plus 1. Again we multiply these two terms and we get minus summation I from 1 to n ai square into I summation I from 1 to n bi square. And we multiply this one and this one, we get summation ai square into summation bi square. Then again what we do, we shall multiply we shall multiply these two terms an plus 1 square into summation bi square. So we get minus an plus 1 square into summation I from 1 to n bi square, and then we shall multiply this term and this term, and we get minus bn plus 1 square into summation I from 1 to n ai square, and then ultimately we shall multiply this one and get minus a n plus 1 square into b n plus 1 square. Now what we do here, then at last we have these two terms. We write it summation I from 1 to n ai bi whole square plus summation I from 1 to n ai square into summation I from 1 to n b I square. And then we see that this one and this one are cancelled, and also this whole square is cancelled with this whole square. So we get minus b n plus 1 whole square into summation a I square, then minus a n plus square into summation b I square, plus 2 times summation I from 1 to n a I b I multiply by a n plus 1 b n plus 1. Remember that these two are also cancelled, means a n plus 1 square into b n plus 1 square, this one is cancelled with the negative of a n plus 1 square into b n plus 1 square. So we have minus b n plus 1 square into a1 square plus a2 square plus and so on a n square. Similarly, we have minus a n plus 1 square into b1 square plus b2 square bn square, and then we have plus 2 times a1 b1 a2 b2 and so on an bn multiply by an plus 1 bn plus 1. If we take common from this entire term, then we see that here inside what we have, the signs are changed, and this is with plus sign, and this one is with the negative of 2 times a1 b1 plus a2 b2 to so on an bn into an plus 1 into bn plus 1. So we just take common negative from all this term, and when we take common, the signs are changed, as you can see here. So the bracket is closed and we have this one. We just take common minus. Now what we have, we again simplify the term inside the bracket and we get bn plus 1 square into a1 square plus bn plus 1 square into a2 square up to so on bn plus 1 square into an square plus an plus 1 square into b1 square plus an plus 1 square into b2 square and so on an plus 1 square into bn square, and then we have minus 2 a1 b1 minus 2 a2 b2 and so on minus 2 an bn, and we have outside an plus 1 into bn plus 1. We just multiply this bn plus 1 square with this bracket, and then we multiply an plus 1 square with this bracket, and then we multiply minus 2 with this bracket, so we get the result here as you can see. Then we have minus bn plus 1 square a1 square plus bn plus 1 square a2 square up to so on bn plus 1 square an square plus an plus 1 square b1 square plus an plus 1 square b2 square plus an plus 1 square bn square, and then what we are going to do here, we shall multiply this bracket with this one, so we get minus 2 times an plus 1 bn plus 1 a1 b1 minus 2 times an plus 1 bn plus 1 a2 b2 minus 2 times an plus 1 bn plus 1 into an bn. So we have eventually minus into, as you can see here, bn plus 1 and a1, and here what we have an plus 1 into b1, and here bn plus 1 into a1 and an plus 1 into b1. So this term plus this term and this term, when we combine them, what we get? We get bn plus 1 into a1 minus an plus 1 into b1 whole square, because these three terms makes a will make a complete square. And see here, I would write again this term and this one, they will make a complete square. So I shall write bn plus 1 into a1 minus an plus 1 into b1 whole square. Similarly, this term bn plus 1 square into a2 square and an plus 1 square into b2 square, and this one, they will make a complete square. When we combine them, we have bn plus 1 into a2 minus an plus 1 into b2 whole square, and so on. We have this one, this term, this term, and this one. These three make up a complete square, and then we have bn plus 1 an minus an plus 1 into bn whole square. So what is this? On the left hand side, we have Sn plus 1 minus Sn. As you can see, this is Sn plus 1 minus Sn. So this whole term, entire term, is less than or equal to 0. So what we have, this implies that Sn plus 1 minus Sn is less than or equal to 0. 0 in a case because this term, this term, and this term, all these terms may be equal to 0. So Sn plus 1 minus Sn may be equal to 0, or if it is not equal to 0, or this one is not equal to 0, I mean, if at least one term, one of them, at least one of them, maybe this one, the first term, maybe the second term, or maybe the third term, or any other term, if at least one of them inside the brackets is not equal to 0, so uh, it means that it means that Sn plus 1 minus Sn is negative. So there are two possibilities, that either we have Sn plus 1 minus Sn is equal to 0, or if inside the bracket, if at least this one or this one or this one, or maybe all of them, if they are not equal to 0, so their square will be positive. And when their square will be positive, and when we all these When we add all these squares, we get Sn plus 1 minus Sn, a negative term due to a negative sign. So there are two possibilities, whether Sn plus 1 minus Sn is equal to 0 or it is less than 0. So this is true for all n. What does it mean? It means that Sn plus 1 less than or equal to Sn for all n. And then we can have Sn is less than or equal to Sn minus 1, because we know that it is true, this one is true for all n. So it means that Sn is less than or equal to Sn minus 1, and Sn minus 1 is less than or equal to Sn minus 2, and so on. So we have this is less than or equal to Sn minus 2, less than or equal to, and so on. This is less than or equal to S2, which is less than or equal to S1. What is S1? In equation 1, here, when n is equal to 1, so what does it mean? Here, when n is equal to 1, here we have AI bi square minus, when n is equal to 1, here we get AI square, and for n is equal to 1 we have bi square. So that's equal to 0. So it means that for n is equal to 1, for n is equal to 1, S1 is equal to 0. S1 is equal to 0 for n is equal to 1. S1 is equal to 0. Okay, because for n is equal to 1, Sn is equal to 0. For n is equal to 1, Sn is equal to 0. As we saw, that's very simple. So this implies that Sn is less than or equal to 0. This implies that what is Sn? What is Sn? Sn is supposed by suppose in the first step when we started here by using equation 1, we suppose that Sn is equal to summation ai bi whole square minus summation ai square into summation bi square. So we have implies that summation I from 1 to n ai bi whole square minus summation I from 1 to n ai square into summation I from 1 to n bi square less than or equal to 0. And this implies that summation I from 1 to n ai bi whole square, and this is less than or equal to, we shift this term on the right hand side, and then we get summation I from 1 to n ai square into summation I from 1 to n bi square, which is our Cauchy-Schwarz inequality, hence proved. So the proof is very simple, and you can see here there is no any difficulty. So this is our required Cauchy-Schwarz inequality by using third method. For Cauchy-Schwarz inequality, it's proof by using first method. You can watch the video, which is Cauchy-Schwarz inequality method 1. So in this video you can learn the proof of this inequality by using first method. Thank you so much.